because after I steps, our subsolution in prims is always a tree. Okay, not in Kruskals it's a forest, in prims it's a tree. Now, S has some more edges. And we're going to say, okay, so if we consider, same thing as before, if we consider an edge and we discard it, then it created a cycle. It connected two vertices that are already in the subsolution. So if we discard an edge, we don't have to worry about it because S couldn't take it either. And I have to reset this, although the next time we run out of time, it'll be the end of the class. So if we discard the edge, our empty subsolution can be extended to an optimal. Before we take any steps, our empty subsolution, yes, can be extended to an optimal solution. Yes. Yes. Here, right. Before we take, any steps. Right. Okay, thanks. If we discard the edge, we don't have a problem. S couldn't take it either. Suppose that we take the edge. If S also takes it, fine, great. Suppose we take the edge and S doesn't take it and takes something else later, which, for example, so it wouldn't happen here in this example with prims if you started A. But it can happen. So what can we say about, well, we imagine S, and let's say that we take this edge and it creates a cycle. Well, can we say the same thing we said before? That the black edges on the cycle have to be at least as expensive as the red edge. No, we can't. Right? Because we're only considering the edges incident to the tree. So is it possible that the red edge has cost 5 and this edge has cost 3? Yes, that can happen, right? Because as we're adding edges to the tree, we get access to edges which are cheaper. So we added this edge AB before we added the edge HG, even though HG is cheaper. So in Kruskal's algorithm, we were considering the edges. Yes. So somebody just wrote, actually everybody can see this, the red edge was cheaper relative to all the edges we were considering at that moment. Yes, but that didn't include this edge. We were not considering this edge. So how are we going to say that we can add this edge and take something away? We can break the cycle, but what? We can't just arbitrarily say, oh, we're going to take any of the black edges in the cycle. So, in this case, then we must remove the edge 3 because it would have been cheaper at that moment. Not quite. Because remember, when we added this edge, we were not considering this edge, and we weren't maybe considering this edge. This could be cheaper than 5 too. This could be cost 2. So we weren't considering this one. So okay, just for the sake of time, I'm gonna, maybe this is what you mean. If you have a cycle, then you've got the tree and then you've got the red edge is incident to the tree, and then you've got some black edges, in this case 2, but maybe more than 2. So this is the cycle, and it touches, right? So you're going to have some green vertex here, and some green vertex here. So the cycle has to leave the tree. At some point, the cycle also gets back to the tree, and then you have some edges in the cycle which are in the tree. So maybe you're not considering these edges yet, because these could be cheaper than this one. Right? This could be 5, and this could be 3. But this one, what? Coupon. Don't know what that is. This edge, there has to be one edge in the cycle, a black edge, that touches the tree, right? Because it's a cycle, it leaves the tree, it has to come back to the tree. So there has to be this edge that reconnects, and this one is incident to the tree when we're considering 5. So that means this edge cannot be cheaper than 5. It doesn't apply to all of the edges in the cycle anymore, but it does apply to this edge. So yes, we can say we're going to add 5 and we're going to take out the black edge in the cycle that's incident to the tree. And that, because we're not processing them always in order of cost, but of all the edges that are incident to the tree after I steps, we're taking the cheapest, and that means that this one couldn't have been cheaper, so we can take that out, and now we get, okay, so now we get a subsolution, and now we get a solution S prime, which is not more expensive than S, and includes the red edge. So we have shown that after I plus 1 steps, our subsolution can be extended to an optimal solution. Therefore, by induction, Prim's algorithm produces an optimal solution. So it's just the exchange argument has to be a little bit more specific about which exchange you do, okay? But you get this nice property that it's always a tree. Now, we have 15, okay, I'm not going to teach you Boruvkas. I'm going to have to leave Boruvkas for the assignment because I want an assignment question. Ooh, maybe I can put it on the exam. Yeah. Okay. So I want to discuss the implementation of these algorithms. And actually, yeah, the implementation of Boruvkas is also kind of sneaky. So that's going to be on either the midterm or the assignment. So Prims is pretty easy to implement as long as you have a priority queue lying around. Right, like a min heap or something like that. Okay, Kruskal's. Let's think. So Prims, you just have your priority queue, and then whenever you add a vertex, so you have a list. Say you have a list of the vertices which are already in your tree. Whenever you add a vertex, then you look at the edges which are incident to that vertex, and you add them to the priority queue if you haven't already, if the other end is not in the list, but actually if the other end was in the list, then you would already have that edge in your priority queue. Prims. Prims. Oh, Boruvka. Yeah, if I put it on the assignment, I'll I think there might be an accent on the U. I'm not gonna, so this is a U and this is a V. I think there might be a little circle above the U or something like that. It's, yeah, it's a Czech or Slovak name. Running out of time. Okay, so it is Boruvka, I guess. Okay, with the U. Okay, so with the dot, with the circle. Okay, so let's talk about Kruskal's. It sounds like it's easy to implement. You just sort and then you process the edges. And for each one, you look at the edge and you decide, oh, does it create a cycle? Now, does it create a cycle in your forest? Now, in Prims, it's always a tree. So what you can do is, when you can, like I was doing, but sometimes forgetting to, whenever I added a vertex to the tree, I colored it. So if you look at an edge, if the two endpoints are colored, then it creates a cycle, right? If one endpoint is colored and one endpoint is not, it does not. And you would never look at an edge where both endpoints are uncolored, unless you're like me and you forget to color the vertices. Now, Kruskal's, you have a forest. So the trees, you know, maybe if you look at two, it's like, well, I visited some vertex and I visited this other vertex, but maybe they're in different trees, in which case it doesn't create a cycle. So how do you tell if an edge creates a cycle? I mean, yes, you can do something like a breadth first search, but this is going to slow down your algorithm, right? I mean, with this example, you can just sort of eyeball it. But last year, I don't know if did I post the videos from last year? Last year, we actually had a case where somebody said, maybe me, add this, and then later we realized that it actually created a cycle. I don't know how we missed it in this small example, but we noticed that, oh, we're going to go and add this, and then we noticed, oh, it actually does create a cycle. Imagine that you have a graph of millions of vertices and hundreds of millions of edges. How do you detect if adding an edge is going to create a cycle? It's not that obvious, right? I mean, yes, if you can do the breadth first traversals or something like that, but this is not going to, you can work out the distance, the connectivities, but that's going to make your algorithm really slow, and it's going to make it much worse than any advantage of just sorting once and not having to keep a priority queue. So in 10 minutes, I'm going to teach you the union find data structure. I'm not going to teach you all of the union find data structure, but so the union find data structure, I think it's by Slater and Tarjan. It's definitely Tarjan. I think it's Tarjan. Maybe it's not Slater. Okay, so the idea is you keep a forest, right? So for every tree in Kruskal's algorithm, you're going to have a tree in this forest, but it's not going to look exactly like the tree in Kruskal's algorithm. Now, so I'm going to have some little trees. Okay. Now, what I'm going to have is, if I have some vertex, and these trees are not going to have constant degree. These trees can have really, really high degree. And in fact, sort of the best case is when they're a root and everything else is the child. So let's suppose, let's make this W. X, and let's make this Y, and let's make this root Z. Okay, so what's going to happen? We're going to call the root, if Y is in the tree that has root at Z, then we're going to say Z is Y's representative. Okay? Now, how, so this is called union find data structure. Now, how do I find, so the find means I give you some vertex and you tell me it's representative. So when I start Kruskal's algorithm, everything is its own tree. So every tree has one vertex, so everything is its own representative. Okay, so now in these trees, the pointers go up. So children point to their parents, and parents don't know about their children. Okay, so the parents just point to their parents, or if they're the root, they point to themselves. Children point to parents, parents don't point to children. Okay, so what's going to happen is if I say find Y, it's going to give me Z. If I say find W, it's going to give me X. Okay, people see how this works? So, how long does it take me to get from Y to Z? Well, it takes me, if there is if Y is Z's grandparent, it takes me two operations. Y looks at its parent. So if I want to find the representative of Y asks its parent looks at its parent, and at its parent, Z is pointing to itself. So Z is the representative. Okay? Yeah, this is going to be a little bit tight. Okay, so W, if I say find W, W is pointing at its parent is pointing at its parent is pointing over here, and this is pointing, and X is pointing to itself. So if I say find W, you walk up, and you find W as the representative. Okay, now, what if I say union W and Y? So this means I'm going to take these two sets, so now I'm adding the edge between W and Y in Kruskal's in the forest, in the minimum spanning tree in the graph. And so now I want these things, they're going to be the same tree. Okay, I'm going to put the trees together. So this is a representation of sets, and I'm unioning two sets. So children point to parents, parents point to either their parents, or if they're the representative, they point to themselves. So everything in the tree points to its parent, and the root points to itself. I have 4 minutes. Okay, so union, you're going to take, when I do two unions, if I say union Y and W, first what I do, I find the representative of Y, I find the representative of W, and then maybe, and then I'm going to make, oh, so that should be red. I'm going to make one of the representatives point to the other one. So if I decide to make X point to Z, now the next time I say find W, what's going to happen? It's going to go here and here and here and here. When it gets to X, it's going to go here, and then it's going to, Z points to itself, so it's going to say, oh, the representative of W is Z. So this sounds really easy, right? I mean, if I say find, you just walk up to the root of the tree. And if I say union, you find the roots of the two trees, and then you make one of them point to the root of the other one. But that sounds like it could be really slow, right? Because if you do this badly, you're going to end up with a degenerate tree, and you're going to have to, if I say, what if I say find W? You walk all the way up. And then I say find W again, you're going to have to walk all the way up. So there are two tricks that make this really fast. So I'm going to need a few extra minutes. People who want to leave at 12:55, please leave. I'm just going to keep recording to actually get this in, because I think we started recording a couple of minutes late. Okay, so there are two. One is, so in the book I think it talks about union by rank. I'm just going to say union by size. So suppose I always take the smaller tree when I do the union, and I'm thinking about whether I should make x point to z or make z point to x. I'm always going to take the smaller tree and make the representative of the smaller tree point to the representative of the bigger tree. So of the smaller tree, point to the root of the bigger tree. So why does that help me? Well, imagine that you're a W, and now you started out with just this one vertex in the tree. So every time you go up, it signifies the time you did a union and you stuck two trees together. I'm going to sneeze again. But okay. And why does W point to this? Because this tree, at the time when you did the union, that tree here was at least as big as W's tree. Now, once you've done the union, this thing, including W, is never going to get any bigger, because you're never going to have anything point to W, because you only ever have a representative point to a representative, and W is not its own representative anymore. So now, if I decide that X is going to point to Z, nobody else is ever going to point to X, only the things that currently do. Okay? So for every step I go up, it means I'm following an arrow, a pointer from a tree to a tree which was at least as big. So because the tree I'm going from doesn't grow after that, the other tree is always going to be at least as big. So that means every time I cross an edge, so for every edge I cross walking up from W to its representative, the size of the subtree rooted at the vertex I'm visiting has to at least double. Because here, W had some little tree. Okay, so W had some little tree, and this now, once I've unioned, this tree was bigger, so that the two trees together are at least twice as big as W's tree. And then this tree has to be at least twice as big again, because this subtree was bigger, this tree was bigger, and then this tree, so that the union of the two was at least twice as big as this tree. So how many times can you double before you get to the root? Well, only log n, right? Like if you have n vertices or n elements in the universe, then how many times can the trees be doubling in size? Log n. So if you do union by size, how long does it take you to walk up to the root? O log n. Okay? So this means union by size, find takes O log n time. There is another trick. So just this is enough for most of the stuff we want. But there is another trick which is called path compression. Which, where did I draw these? So when you're going up from W to Z, what you're going to do, okay. You have X, and then you have all these vertices on the path from W to Z. When you walk up, after you walk up, you walk back down, and each of these is now going to point directly to Z. Right? So you're never going to walk from W to what was its parent ever again. This trick is called path compression. And with this trick, it turns out that you get, I don't know if you've seen amortized analysis. I don't have time to teach it to you now because I'm over time. Maybe it can be in the tutorial. Yes, let's put it in the tutorial. Yes, that will be good. Path compression, you do this trick with path compression, then you can show that you get amortized, not worst case, but amortized O log n. Actually, in fact, you get something called log star n. Log star is called the iterated logarithm. And it means the number of times you have to take a log to get down to 1. So this isn't going to fit in this class. This is going to have to go a bit into the tutorial. So you get amortized log star n time. This is in the book, and it will be in the lecture notes. And then in fact, you get something called, it's actually even better than that. It's something called inverse Ackermann, which is alpha. So it's not constant, but it's as close to constant as you could ever possibly want. So it's amortized. So M operations, you get, for M operations, you get inverse Ackermann Mn. So it's very, very close to constant. But proving that is not easy. It's not in the book. In the book, I think they just prove log star. I'm not going to prove it in the course notes. Okay, so that's how you implement Kruskal's. Questions? Is anybody still here? $22 people. When is assignment 8 as the solutions? I think some people who have extensions are still turning it in tonight. So I haven't written the solutions. I wrote like a draft of the solutions, but I have to write them actually up as solution key. It will be, I have to give a talk tomorrow. So that's why I'm a bit behind. I was preparing slides.